Hey guys, welcome back to quantum mechanics. So last time we had started our discussion on time-dependent perturbation theory, and what we basically did was work out kind of the traditional formalism for time-dependent perturbation theory. So the basic idea is that you have a Hamiltonian that you can split into a simple piece and a small piece, and now the small piece has some time dependence, whether it's some type of like sudden, where you like basically flip a switch and a perturbation comes on, or if it's something more gradual like an adiabatic, or if it's sinusoidal. But the whole idea is that the time dependence of your Hamiltonian is all in the perturbation piece. And so the main question that you're looking to answer in these types of problems is what's the probability that you have some system that's initially in some state I, and then you turn on your perturbation, and then you want to see if the state has made a transition during some time t. And so the idea is to basically compute the overlap coefficients, really the coefficients that come from the overlap of the initial and final states. So our Hamiltonian, like I said, is you can split it into the simple and the small piece, but now the small piece depends on time. And so we have a couple of sources of time dependence. So there's the time dependence that's coming in from the Hamiltonian that we're introducing, but we also know that there's time dependent states, right, as time evolves. We talked a lot about that last semester when we introduced this idea of time evolution operators, right? So there's going to be some time dependence coming from time evolution operator, and then the time dependence coming from our perturbation Hamiltonian, right? So the idea, like I said, is we want to compute probabilities for transitions, and these probabilities are given by basically the modulus squared of these coefficients. So we were trying to determine these coefficients, right? And so what we did was we started with the Schrodinger equation for some general state alpha, right? That has some time dependence t. And so we expanded this state in our usual way, right? Where the time dependence, some time dependence in these coefficients. And we went through some algebraic tricks, and we basically found that we could write down kind of a differential equation for these coefficients, right? So it's like a Schrodinger-like equation for these coefficients, and on the left-hand side you got the time derivative, on the right-hand side you got the matrix element of your perturbation Hamiltonian. All right, and the problem is that the equation looks harmless, but it's an infinite sequence, right? So there's in general there's an infinite number of these final states that you could have, and so these are coupled an infinite number of equations, which is not an easy thing to solve. So what we try to do is again use perturbation theory. So we're assuming that H1 is small, right? And if that's the case, then at zeroth order we have the time derivative of being zero, but then the higher order terms are should get smaller and smaller, and so you can do a perturbative expansion. So we tried that, so we plugged that in, and what we found was that we could break that infinite, those infinite coupled equations into different pieces by matching orders of our powers of our perturbation. Right, so like at zeroth order, you find the coefficient's a constant. In other words, it's just the identity operator, right? And then at first order, you have a differential equation that depends on that perturbation Hamiltonian, but now you're feeding in the zeroth order term, right? And that's the way it works. It kind of bootstraps its way up. So the second order coefficient will depend on the first order coefficient, so on and so forth. Okay, and so we worked through, and we found that, so like I said, at zeroth order, you just get the delta function. At first order, in general, you get some equation that looks like this, right, where The time dependence coming from just your normal time evolution is kind of captured in this exponential, right? And that's the idea. So the idea is that you get the first order, and then you can feed that in and compute the second order coefficient, and so on and so forth. And then you'd put them all back together if you wanted to compute the probability and take the modulus squared, right, of the sum of those coefficients. And then we worked through an example at the end. What was it? It was a simple harmonic oscillator that we applied some perturbation due to an electric field, right? This electric field has some type of exponentially decaying time dependence. And so I don't want to go through that again. But okay, so that was, like I said, that's the traditional way of doing time-dependent perturbation theory. And what I want to do today is talk a little more abstractly, I guess, talk about in a more formal way a different approach to time-dependent perturbation theory. And this is kind of analogous to, last semester when we talked about time evolution. And, the traditional way when you're studying wave mechanics is to, just solve the time-dependent Schrodinger equation, right, for your wave function, whatever, with whatever your Hamiltonian is. But we found that there's another way that you can do it. It's actually a more fundamental way, and that is through the introduction of the time evolution operator, right? And so the basic idea is that you solve for the time evolution operator, and then, if you're given some state, then you can always find the state at some later time by just applying this time evolution operator. So we're going to try to do the same thing, but now we're going to have some added time dependence coming from our perturbation. Okay, and what it's going to lead us to is another picture, if you will, like picture in quotation marks, of time evolution. Okay, so like I said, the traditional way of doing time-dependent perturbation theory we covered last time, and if we wanted to, we could just keep applying this same recipe. But what we want to do today, like I said, is look for a more kind of abstract and really a more compact formalism. And what it'll do is, we'll gain some insight into what I call the anatomy of the perturbation series. But really what it's going to do is it's going to set up a nice formalism for us to use with scattering theory, which is going to be our next big topic. Okay. So the idea of this formalism is that, like I said, we have two sources of time dependence here. We've got the time dependence coming from just the normal time evolution, right? So the normal the time evolution that we talked about last semester, but we've also got time evolution that's being generated by the perturbation, right? And what we're going to do is we want to try to separate these two time dependencies. And since we know that the time the time dependence coming from H naughts are going to cause any transitions, we would like to work in a picture where we can just focus on the time dependence coming from the perturbation and forget about the time dependence coming from this guy, from the unperturbed Hamiltonian. All right, so to do this, like I said, we're going to have to introduce another picture of time evolution. And just to remind you, so last semester we saw two different pictures, right? So we talked about the Schrodinger picture, and so in the Schrodinger picture, your state cuts or your wave functions evolve with time, but operators are assumed to be time independent or constant in time, right? But then we saw that in some cases it's more advantageous or easier to work in what's called the Heisenberg picture. And this is where you have state cuts being constant time, but now operators evolve with time. And because operators are evolving with time, it basically leads to the fact that the base cuts themselves have to evolve with time in a way such that they cancel out some of the time dependence in the operators, right? But the main idea is, like I said, they're just different ways of going about computing the same things, right? And so these pictures are what we would call equivalent. In other words, they're going to predict the same physics. If you apply them correctly, you're going to get the same physics results. It's just, in some cases it's easier to work in the Schrodinger picture. In some cases it's easier to work in the Heisenberg picture. All right, so the main thing that we're after are probabilities. And so independent of whatever picture you're working in, the probability that you compute should be the same thing, whether you're working in the Schrodinger picture or the Heisenberg picture. All right, so in the Schrodinger picture, remember, time evolution is just given by the normal Schrodinger equation, right? And if we want to talk about, in our case where we have a time-dependent perturbation, our Hamiltonian is going to be made up of the small piece and the perturbation piece that depends on time. And what we did last semester was see that, we could actually work with a more fundamental equation by introducing this idea of the propagator or the time evolution operator, right? So we said, okay, well, our time-dependent state is basically defined as whatever the state was initially, and then some operator u that evolves the state in time, right? And so if we plug that in, what it allows us to do is cancel off from both sides this initial piece. And so we're able to write down an equation, Schrodinger-like equation, but for the time evolution operator, right? And this allows us to, again, solve for the time evolution operator, and then if we want some state at some later time t, we don't have to solve, we don't have to solve the time-dependent Schrodinger equation for the wave function. We can just apply our time evolution operator given the initial state. What else? So there's some properties of this time evolution operator that we discussed last semester. One is that it has to be unitary, right? That's always comes back to the fact that we don't want to screw up the conservation of probability. It has a compositional rule. In other words, so if I take two time evolutions, say from T1 to T2, and then I evolve from T2 to T3, it has to be equivalent to just one time evolution from, say, T1 to T3. These things are what are called continuously connected to the identity operator, meaning that if I take the limit of T2 goes to T1, this thing better just reduce back to the identity operator, right? And then finally, this kind of hermiticity rule, which says that the Hermitian conjugate is the same as reversing the operation of u. So in other words, if I take time evolution from T2 to T1, but take the Hermitian conjugate of it, it's the same thing as taking the time evolution from T1 to T2. Okay. All right. So what we want to do, like I said, is today, instead of working in the Schrodinger-Heisenberg picture, develop a new picture where basically we just isolate the time dependence coming from the perturbation. Okay. And for reasons that'll become clear later, this picture is called the interaction picture. Okay. And so basically what we want to do is, or the way we want to envision this is to recall, the fact that unitary operators or time evolution operators, we can always generalize or basically come from the generalization of a rotation operator, right? So in normal Euclidean space, right, these operators rotate the state into another state, right? And in time evolution, or even, when we talked about spatial translation and rotations, like angular momentum, we saw that we could use this same idea, right? So we could take our state that starts out at T0 and apply this operator, and it would give us some new state, right, at some later time T, or at some, spatially translated position. Right, so we can always think of time evolution of state vectors as rotations in our Hilbert space, right? And so this rotation is generated by our normal, time evolution operator. Or if you want, remember that this guy depends on the Hamiltonian, so it's going to depend on two pieces, right? The time independent symbol piece, an unperturbed piece, and a time dependent piece, right, which is our perturbation. And so in the case where we turn the perturbation off, right, we're back to what we had last semester, right? So we just basically have this nice Schrodinger equation for our operator, our time evolution operator. And we know that this unperturbed piece is independent of time, so we can solve this equation by just separating and integrating, and that's where the normal simple expression for the time evolution operator, that's where that comes from. But what we're doing now is we're adding this time dependent perturbation piece, and so what we're going to have is now that both this guy, the unperturbed piece, and the perturbation piece are going to jointly produce the rotation. In other words, they're both going to contribute to time evolution, right? But we know that the time evolution coming from the unperturbed piece doesn't produce any transitions between the eigenstates, right? And in fact, when we're doing these type of analyses, it's just, if you wanted to keep that time dependence coming from that guy, you could, but it just gets to be kind of an annoying factor, right? Because what we're trying to assess are these transition probabilities, right? And so what we want in order to do that is the time dependence coming from this perturbation, because that's the only piece that's going to cause these transitions. All right, so what we want to do is to define a new picture, right? Our interaction picture, such that the only time dependence is coming from the perturbation piece, right? And the way that we do that is to, use this rotation analogy and just imagine doing a transformation where now we've transformed, because remember, the time evolution we can think of as the vector in our Hilbert space is rotating, because of the time evolution. And so what we do is we basically do a transformation so that we're sitting on that vector. And so the only time evolution that we really observe is the time evolution coming from the perturbation piece, right? So to us, the time evolution coming from the unperturbed piece is non-existent, right? We can't observe that. The only time dependence we see is coming from the perturbation piece, right? And so you can think of this as being in a new frame of reference, if you will, or really just think of it as like I said, a different picture of time evolution, right? In the end, it shouldn't depend, our answers that we compute for these probabilities shouldn't depend on which picture we're in, all right? This is just a nice compact formalism for doing these things, and it'll become more handy when we get to scattering theory, okay? All right, so basically what we're going to do is we're going to define some new state kets, right? And these guys are going to depend on time, okay? So it's kind of like the Schrodinger picture, right? But the difference is that we're going to basically kill off the time dependence that's coming from the unperturbed Hamiltonian, right? And the way that we do that, remember that this guy is being involved with this operator, right? And the way that we kill off that piece is by hitting this with the Hermitian conjugate of the time evolution operator, right? The unperturbed piece, right? So that should kill off that dependence. And so what we'll have by definition is some state ket that's only time dependence is coming from the perturbation piece, right? And we know that, like I said, if we took the limit of t goes to t naught, the initial time that this thing reduces to the identity operator, and so in that case, or in that point in time, the two frames are identical, right? And we've talked about this when we talked about the relationship between the Heisenberg and Schrodinger pictures. Okay. So, right. So now the time evolution of the state ket, right, we can write down in terms of a Schrodinger-like equation. Okay, so we have our left-hand side of the Schrodinger equation. And what I want to do is take this guy and plug in our definition in terms of the Schrodinger picture quantities, right? And then take take the derivative inside here, right? So I'll have one derivative term hitting the time evolution operator, and then I'll have another derivative term where it's hitting the Schrodinger state ket, right? But what I can do is use the Schrodinger equation for this guy and the Schrodinger equation for this guy to replace those derivatives with terms that look like the Hamiltonian hitting this hitting our time evolution operator, right? And I can do the same thing over here. The difference is that now the Hamiltonian that we're plugging in here contains not only the unperturbed piece, but our perturbation term as well. Okay. And if I do that, what I find is that this piece cancels off this piece. And what I'm left with basically is a Schrodinger-like equation. So I have this equation over here. I have this piece over here on the left-hand side. And on the right-hand side, the only thing that survives is this guy. Right? But now what I can do is, I just noticed that this should be, so this guy should be to the right of this operator. But what I can do is multiply by 1 in the form of US times US dagger, right? And what this does, US dagger, when it hits this psi s, right, that's the definition of our psi I, our interaction picture state ket. And then if I define the combination of US 0 dagger, HS1, and US 0 as some new Hamiltonian, interaction Hamiltonian, then I can rewrite that equation and our interaction picture as just a normal Schrodinger-like equation, right? Where now everything has the subscript I telling us that we're in this interaction picture. Okay. All right. And just, it can't be stressed enough that this picture is equivalent to the Schrodinger or the Heisenberg picture in the sense that the physics predictions are going to be identical. You know, the big difference is that now when we're going through and trying to isolate time dependence of, or trying to compute the transition probabilities, we're not going to have to carry around that annoying, time dependence coming from just the normal time evolution of the state. Let's see. Okay, so we know that in the Schrodinger picture, the state kets evolve with time, but operators are constant, right? And in the Heisenberg picture, state kets are constant in time, and operators evolve with time, right? The interaction picture is kind of a mix of the two. So in the interaction picture, both the state ket and the eigenkets evolve with time. Right, so we can see that from our definition of this guy, of how we define the interaction picture. But it turns out that you need the state kets as well to evolve with time. Let's see, what else I want to say. So we know that the state kets and the base kets or the eigenkets both evolve with time. What about operators? Well, it turns out that the operators also evolve with time. So like I said, this is kind of a mixture of the Schrodinger and the Heisenberg pictures. All right, so we would have some operator AI, and this thing's defined much like, the way we defined the Heisenberg picture operators, right? It's defined in terms of the Schrodinger picture operator being sandwiched between these two time evolution operators, right? what am I saying here? Yeah. Okay, so we can work out how this guy operates when it hits one of the interaction picture cats. All right, so I can rewrite this AI in terms of its definition in terms of the Schrodinger picture. All right, and then rewrite my AI cat in terms of the Schrodinger picture cats. And these two guys are going to cancel each other out. So I'm left with AS hitting the AS or the Schrodinger picture ket. All right, that'll give me the eigenvalue back out, and what I have left is this U dagger hitting this AS, and that's just the definition of AI. All right, so what we find is that we can write down a nice eigenvalue equation in this picture for our time-dependent operators. And so having that, now you can say, okay, well, how does this thing evolve with time? Right. So what I want to do is start with my definition of AI in terms of the Schrodinger picture operator and the unitary the time evolution operators, and take a derivative. Right. And so I'm taking a derivative of this full thing here, but the only two things that depend on time are two factors of the time evolution operator. All right, so I can take this derivative, I get two terms, and now I can do what I did above, which is take these derivatives and replace them with basically the right-hand side of the Schrodinger equation, right? So the piece that's the Hamiltonian operating on this time evolution operator, and likewise for this term, right? And so if you recall how we computed the Heisenberg equation of motion in the Heisenberg picture, this should look familiar to you, okay? So you can multiply this all out, and what you find is that you get this this term here, which is basically just the commutator between our Schrodinger picture operator and our Schrodinger picture Hamiltonian, right? But these guys, when you sandwich them between our US and our US dagger, are nothing but the interaction picture operators, right? So what we find is that in the interaction picture, the time evolution of these operators basically is just given by a Heisenberg-like equation, right? Operators evolve in response to the unperturbed. Yeah. Okay. Okay. So now that we've got this new picture, it'd be good to check and make sure that the expression that we computed last time for our coefficient using this kind of traditional way, make sure we can still reproduce that. Okay. And so what we're going to do is try to develop a perturbation series or perturbative series for the transition amplitude, right, from some state I to some state F. So we can define, again, we start by defining the propagator in this interaction picture to be, its action. What it does is it operates on our initial interaction picture ket and gives us the ket at some later time t, right? And we've already seen that this thing, you can compute it. If you know what the interaction picture or what the perturbation Hamiltonian is, you can actually compute this guy by just solving the Schrodinger-like equation, right? And then just like we did before, like once you find what UI is, and you can easily go back to the Schrodinger picture, right? Because we know what the relationship is between UI and US, right? All right, so the kind of unfortunate thing in this interaction picture is that because H1 or HI, our interaction picture Hamiltonian, depends on time by construction, but we're never going to have a situation where the solution is going to be, nice and like we can't just separate this and integrate it, assuming that this thing's independent of time and get the usual e to the minus I ht or whatever. We're always going to have the case where HI is going to depend on time. So we're always going to end up with these type of integral type equations. All right, so we'll have to plug in our Hamiltonian and do this integration. Right. So in other words, so the formal solution that we'll have is going to look something like this. Right. So we'll have some piece we've always said that this thing is continuously connected to the identity operator, and then our perturbation piece here, right? And this will be the piece that we expand. So yeah, that's just a check on what I was just saying. Okay, so the problem here is that this thing is, you know, in the technical sense, is not really a solution because UI appears on both sides, right? So what we're going to have to do is, like I said, we're going to have to expand this term, right, in a perturbative series, and then do the normal thing of matching orders. Okay. Right. So it looks like we haven't really made any progress, right? With that, we've introduced this new picture, but now we still, our solution, the prospects of our solution look a little gloomy, right? But like I said, this integral equation gives us a nice way to carry out this perturbative expansion. All right, so let's say, okay, let's just start by at zeroth order and say, all right, so I want the interaction picture time evolution operator to zeroth order. All right, so that part is easy because if I'm talking about zeroth order, then I can just say, okay, this term, I can drop it, right? So I drop that term, and then I find that the time evolution operator is just the identity operator. Okay, so that's the easy one. Where am I? Yeah. Okay, so the time evolution operator to zeroth order is just the identity operator, right? But now let's go to first order. Okay, and again, what we're going to do is expand this guy, right, in a perturbative series. All right, so if I want the first order term, the Hamiltonian's already first order, so that means I have to keep only the zeroth order term coming from this expansion. Right, and the zeroth order term we've already seen is just the identity operator. All right, so what I have at first order is something like what we had before. So it's the identity operator and then minus the integral of the Hamiltonian, whatever the Hamiltonian is. Okay. And to see what we want to see is that, if we take this kind of route in computing these time-dependent perturbations, can we get to the coefficient, the same expression that we had for the coefficient last time, so to first order. So that last time, just to remind you, we found something that looks like this, right? And if we work to all orders, so this coefficient, remember, it's just the overlap between the final state and the initial state. Right, the final state has this term. This is just the time evolution operator hitting this guy, and over here we have the time evolution operator hitting this guy. I can work backwards, right, and rewrite this in terms of US dagger and US, right? But we know that this combination, right, is nothing but our interaction picture time evolution operator, right? So what we can do is feed in, now that we have this expression for this coefficient in the interaction picture, we can plug in our first order expression for this guy, right? And if I do that, so here's what I'm doing. I'm plugging this first order. So here's the zeroth order of the first order piece, right? And now I want to take, bring these broads and kets in, right? So this guy, when it hits this guy, is going to give me a delta function, right? In this term, right? So it's going to give me a delta function. And then I'm going to have, when I bring these in, I'm going to have the matrix elements of the HI with these guys, right? But I want to try to show that it's equivalent to what we did before. So I'm going to take our HI, or interaction picture Hamiltonian, and express it in terms of the Schrodinger picture, right? So when I do that, I have my Schrodinger picture Hamiltonian, I've got my 2 time evolution operators in the Schrodinger picture. But now these things, when they operate on this guy, are going to give me exponential factors, right? Because I know what this thing looks like, because our unperturbed Hamiltonian is independent of time, right? So we know what the time evolution operator looks like, right? And so what I end up with is this first order term that looks like the matrix element of our perturbation piece times this time evolution piece, and we're integrating over it, right? And if you go back and compare with what we had before, you see that that we can indeed reproduce our expressions for our coefficients using this interaction picture. Okay, at this point it might seem like overkill because we've already done it, but like I said, this interaction picture is going to make our lives a little bit easier when we try to tackle scattering theory. Okay, so the way that you do this is now, so basically you have to kind of recursively plug in, when you want to compute the time evolution operator to higher orders, you have to basically kind of recursively feed back in the solution, right? So in the end, the interaction picture time evolution operator looks like a perturbative series, but it's a perturbative kind of integral series. So you have, the 0th order term. Here's the 1st order term that we just computed, right? And then you would feed back the 1st order term into your general expression to get the 2nd order term, right? So 2nd order, you're going to have 2 factors of the interaction Hamiltonian. They're going to be at different times. You're going to have to integrate over those 2 different times. And the 3rd order term, and so on and so forth, right? And if you remember when we first introduced, or last semester when we first talked about time evolution, we talked about these different cases, right? And this is what we called, at the time, I jokingly called it the nightmare scenario. So this is where you have a Hamiltonian that depends on time, right? But the Hamiltonian at different times doesn't necessarily commute with itself. And what you end up with is what this thing, this series, which is called the Dyson series, right? So I don't know if that rings a bell or not. But we talked about it last time, or last semester. I just introduced it and I said that we would talk about it this semester. And so here it is. Okay. So that's it for today. And we'll pick up using this formalism and keep talking about time-dependent perturbation theory as we work our way towards, this bigger goal of starting to talk about scattering theory. All right, so I'll see you next time.